And I am now recording. Wait, what is this recording this? Here we go. Good. And we're rolling. So we just finished talking about motion in terms of work and energy. And the idea there was that if you applied a force, perfectly terrible pen, this thing again. Okay, when you apply a force, for example, on something, and you apply that force over a distance, okay, a force over a distance, well, that's what work is. We found work is force times distance. And we found that this concept changed kinetic energy. And because kinetic energy contains velocity in it, this means that we can figure out how much the velocity changes by knowing how much force was exerted over what distance. And we looked at this in different ways, including looking at through the conservation of energy. Now, as we pointed out when we started this conversation, of course, if you're exerting a force on an object for a certain distance, well, that's going to take a certain time as well, because obviously we're pushing this thing over a certain distance. And by the time it's over here, it's traveled a certain distance d in a time t. So both d and t are required for that force to act. You can't have a force act instantaneously to change velocity, and you can't have it act instantaneously in space either. It needs distance to change it as well as time. So we can look at that process we just looked at, not in terms of how the distance is required, but we can also look at this process from the perspective of, okay, we need to apply that force for a certain time. And let's just assume for a minute that just like here we had average force, that we're going to look at a constant force or average force, and this time we're going to look at it for a certain time. And if we do that, then we have one important difference here right away, which is that when we apply the force for a distance, we ended up with a number, energy, a scalar in joules, whereas here, what we're doing now is we're applying a force, which is a vector quantity, for a certain time, which is a scalar or just a number. So a number times a vector, that's still a vector. So we're going to now get a change out or a different quantity, but this quantity will be a vector, not a scalar. So what does this mean? That means in parallel to this, we have two new concepts. Well, first of all, we're changing something, and that thing we're changing, we're going to call momentum. So just like we had kinetic energy before, 1/2 mv squared, unnecessarily small written there, and I'm going to write it bigger because that's just stupid. So here we go. I'm going to write it bigger there because you can't see it. K is 1/2 mv squared. That was the thing we changed with work. We changed kinetic energy. And now we're introducing this new concept of momentum. And momentum is m times v, velocity. Mass times velocity is momentum. And this thing that we're applying to it changes it, just like work changed the kinetic energy. And now we need a name, of course, for that in parallel as well, because work was the thing we called that changes kinetic energy. The thing that changes momentum, we will call impulse, J, impulse. Impulse, and this was work. But the same thing absolutely in parallel applies. So work, which is a force for a distance, changes kinetic energy. And impulse which is force for a time, changes changes momentum. Okay, so the two concepts are working hand in hand. They're really the same thing. And just to repeat from the beginning, of course, while we apply this force on this, let's say, cart, right? So this is our hand applying that force for a distance d. Of course, it takes a time t to do that. So it's still the same process. And we can look at the process from the work kinetic energy perspective, or we can look at the process from the impulse momentum perspective, and the two go together hand in hand and they'll apply equally. But the question is, sometimes this approach is going to be much more helpful for us to be able to come to the conclusion that we want to figure out, such as when we're looking at a roller coaster. This is a great approach. And other times, this approach is better for us to figure out what we want to figure out. In that case, we'll talk about momentum, and impulse rather than about kinetic energy and work. And we're going to take a look at some examples where this applies right now. So that was the super intro. And did you guys have any questions so far? Or are you guys okay?
All good.
Sorry to make this kind of front and center, but I think it's going to be easier to run it this way, especially if we're recording it. So I'm going to now look at examples of where impulse and momentum are the appropriate choice. Okay, and before I do that, I'm going to take a picture of this. Oh wow, the picture is hilarious. It's like God speaking to you. Oh my. Okay. All right. Let me get a picture of that, and I'll post it to the group. There we go. All right. There we go. Sweet. So, let's kind of review where we are. We introduced the concept of, that one doesn't work right. We introduced the concept of momentum. There we go. And we also introduced the concept of momentum change occurring when impulse occurs. Okay. We also introduced the idea that this concept of impulse for a constant force, right? That's pretty, let's do it over here. For a constant force, similar to work, for a constant force, work is just force times distance. So here the same applies here, where it's simply F times how long you apply the force. And then technically, to make this right, this has got to be the average force. That's true. So by definition, almost, you can call this the definition of average force. The impulse is equal to how much average force we have times time, just like work is average force times distance. And of course, just as for force, which is applied over a distance, we then talked about how to use an F versus X graph to get how much impulse is, how much work is done. The same thing, of course, applies here. If we now look at an F versus T graph, how does the force vary through time? Then that means that we can find impulse by finding the area under it again, like we found work for the area underneath the force versus X graph. Now, because we're in AP Physics 1, we will not be required to actually find that area using calculus. because that's beyond the scope of the class, but in AP Physics C last year for the seniors and next year for the juniors, that's something that was part of the curriculum. But so if we look at this thing here, and we have here we go, here's our F graph, we can say, okay, so underneath here, this is the impulse provided to the object, the area underneath that graph. And in this class, in AP Physics 1, you would only be asked to find this area if you can use either just counting little boxes, like if this was given on a notebook piece of paper, or if it was a certain shape that allows you to find it, such as a triangle or something like that, where you don't have to use calculus. Now, this is where we are right now. And now let's apply that concept to a situation where this is really important. So we're going to pretend, I'm sure you guys are all really, really good drivers. And if you're not drivers yet, I'm sure you'll be really good drivers in the future. But let's pretend that one of you is not a good driver. And because you're an American, you're driving an obscenely large vehicle. There we go. Now, nobody will get hurt in this fake collision. We're just going to point that out. But we're going to have a collision between this careless driver driving an unusually large vehicle because they're American. And I'm just going to nominate somebody for that. Who seems like somebody who might be driving such a vehicle? Who's like the most American kid we got? Is it like Alex? Alex? Okay, so we got Alex. Alex is driving this thing. And Alex is, you know, doing the American thing, eating a sandwich, drinking a 64-ounce soda, changing the CDs, trying to get his MP3 player attached, making 3 phone calls, and just dropped, I don't know, something on the ground. He's not paying attention anyway. So he's just cruising along, not paying attention, and he will have a collision over here. And we're going to put over here at the red light, right? We'll put over here a law-abiding European in a European-sized vehicle. So here's the European-sized vehicle. Here we go. And it looks a little weird. Maybe like who should we have here? How about Octave sitting in a little Peugeot or something like that? Does that sound like a reasonable solution to this problem? Okay, so we've got always. Okay, so we've got Octave here. And Octave, of course, is an excellent driver and driving a reasonably sized French vehicle, trying to support the French economy. And he's not moving in his Peugeot, whereas Alex's Hummer is humming along. And Octave is not moving in his small car. And Alex is moving with his car. And he's going, let's say, 50 kilometers per hour.
That's pretty mild.
That sounds good. Not good for Octave, but okay. And let's talk about the masses. Like I said, American vehicles tend to be obscenely large. So let's go with the mass of the Hummer here as 3,000 kilos. That sounds reasonable. They might even be larger. I really don't know, but they are very big vehicles. Whereas little Peugeot might be maybe 900 kilos. That seems reasonable. It's a small one. So let's go over here with the mass of the Peugeot being 900 kilograms. Now, as we now go into the collision, and nobody gets hurt, just to make sure these are well-equipped vehicles with airbags and all that stuff, we need to think about what's going to happen in terms of the forces, okay? And we can make a little graph over here. We can make a graph for the force on each object, okay? And we can say, all right, well, let's think about what's going to happen to the force on the Peugeot, on VPO, and then here we have VHO. The force on the Peugeot when it's struck by the Hummer. So it's difficult. This is actually a really, really complicated problem if you were to do it in detail. So if you were to actually put a nice little force sensor on the Hummer and a force sensor on the Peugeot, and you actually go through this crash, we can imagine what it will be like, but we have a hard time estimating like what the maximum force would be, for example. It's going to be big, but how big is it? How long is it going to take? How does it change? Those are all difficult questions, but we do know a few things. We know for one thing that before Octave's car is struck by the Hummer, there's no force acting on it. It's just sitting there and waiting. And then once contact is initiated, it goes up, right? Because initially this bumper just touches the Peugeot's bumper. And there's at first zero and then some force, and the force gets bigger and bigger as more of the Peugeot gets embedded in the grille of the Hummer. You can kind of imagine this. So the force goes up, and then eventually the two cars are traveling together. And of course, as they then are traveling together, there is no longer any additional force acting on the Peugeot because it's no longer accelerating. It's not moving, and then it is moving at that maximum speed that it reaches once it's embedded in the Hummer. So that means it would go up in terms of its force, reach some maximum value, and then kind of dip down again. And this whole process goes very, very fast. If you've ever been in a car crash, you know they're ridiculously fast. You're like, boom, you're like, oh crap, man. So it's like 0.1 seconds. I don't know. It's a very, very short time that passes. It's very, very short. Now, if you look at these two graphs and you say, okay, well, what does that tell us? Well, about this other force on the Hummer. Well, the force on the Hummer, now it acts not to the right. FP is to the right because Octave gets accelerated to the right. Alex was moving to the right, and as he was moving to the right, but he gets slower, right, in the collision because this block will act against it, this Peugeot, and therefore the force on Alex will be to the left, Alex's car. You might be like, oh, but how big is it? Well, we don't know again, but we do know how big it is compared to this force because we've studied how two objects interact, and Newton's third law says that the force exerted by one object on the other is equal and opposite to the force exerted by that other object back on the first. So that means, oh, I could have done colors. That would have been good. Oh, yeah, let's do that. So I'm going to change the color here. That's a good idea. So here, in honor of the, here we go. Here we go. So there's that car. It's blue, that force. And now the force acting on Alex is, again, 0 to start with. And then it kind of dips down to the exact opposite of that. You might be like, okay, but how is that helpful? Well, it's helpful because if we now take the two forces and we add them together, okay, and we say, well, what's the force on the Peugeot and the Hummer together? What if we think of both of those objects together and ask, what's the total force on the Peugeot and Hummer in total? And then we'll end up, oh, purple. That makes sense because red plus blue is purple. Wow, this is pedagogy by colors. You are so having fun with the colors. So we've got our graph. Here's F, H. Oh, I could do this red. That's a good idea. Here we go. So we're going to go on here and say F, H plus F P, and that's equal to, I don't know how that color of white that shows up, but we're gonna call that F. It's supposed to be purple. It's not as pretty as I was hoping, but it's okay. So here's the total force. Oh, total sounds like they're dead now. That's bad. Total. Okay, so the total force would then be something like this. It's exactly opposite to that. So when you add them together, this entire time, the total force on the Hummer and Peugeot together is 0. Well, that's awesome Because if we make the total force equal to 0, that means that if we look at our equation and say how much impulse is delivered, well, the average force is constant, it's 0. So that means the impulse delivered during this collision to the Peugeot Hummer system is a big fat 0. And of course, if impulse delivered is 0, that means the change in momentum is 0, and therefore momentum is conserved. Okay, so what do we find? We find that in this collision, and really for all practical purposes, in all collisions, at least for AP Physics 1, because you'll see that anytime there's a collision, you have to think, momentum conservation, and we'll explain why. Only internal forces matter, so momentum, total momentum is conserved. So we're physicists, so we can look at this statement and feel very comfortable about it, even though, of course, technically, there are some external forces acting that are small, but they're there. So as Alex hits Octave's car, they slide across the surface, and there's friction force here. But it doesn't have much distance to act over or merit much time. And that force is very, very low. And I think this is not surprising. So, in this situation, the asphalt is not very helpful or hurtful to Octave. It's really all about the Hummer. I think that's not surprising. And you're not really concerned about knowing that coefficient of friction. It's not like if this was on ice, this would be better or much worse, because it's really about all the oomph of the Hummer hitting the cute little car. Well, it was cute until it got struck. Now, that having been, we're going to push now, a little down. We're going to take a picture of that. And then we're going to actually come to the answer of the problem, which now becomes surprisingly straightforward. Okay, so we have it now stated out here. In collisions, only internal forces matter, so total momentum is conserved. Let's apply that concept to our specific situation. So we're going to erase this stuff down here and then just go right in here and use that to find the answer. So let's take a look. Initially, only Alex's car is moving, so the initial momentum resides completely with his car. It's his speed times his mass. So M Hummer times V Hummer 0. And the nice thing here is, because we are setting two sides equal, we don't have to worry about units. So you don't have to convert this to meters per second, because we'd like to have our final answer in kilometers per hour as well. So we can leave it like this. So let's plug that in. We got 3,000 kilos. We got 50 kilometers per hour. And we get out an answer of 150,000 kilograms times kilometers per hour. This is the momentum before the Hummer strikes the Peugeot, and after the collision has occurred right afterwards. So like thousandth of a second right after the collision is complete and the two cars are sliding together into this intersection now, the total momentum is the same because in the collision, only the internal forces matter. So we have 150,000 kilometers per hour as the initial momentum, but that's actually also equal to the total momentum afterwards without the subscript, 0 for before and no subscript for after. And of course, afterwards, well, what do we have moving? Well, both. So this is now the total mass times the final speed. Two cars move together. Octave's Peugeot is 900 kilograms. The Hummer is at 3,900. So this allows us to now find the final speed because the final speed is the only variable in this equation. Let's write down the 150,000 over here. 150,000. And now we can solve it. Am I still on the screen? I sure am. So here we go.